Well, let's talk about the second law, actually look at the second law today. So we've been talking about kind of the standard thing we would normally do in a thermotext. We've introduced these simple cyclic devices, one being the heat engine. So the heat engine is the device that takes heat from a high temperature source into a boiler. So we get high pressure, high temperature steam coming out of that, run that into a turbine or turbine. That's going to generate a power output. From the turbine, we're going to get low pressure, low temperature working fluid. We're going to run that through a condenser. Most modern steam engines, we want to go ahead and get that all the way down to a liquid because I need high pressure up here. Well, there's nothing in the boiler that's going to increase the pressure, so I need to put just a little bit of work into a pump, just a little bit of power input into a pump. That's going to generate high pressure liquid to go into the boiler to be boiled off. And again, we can't turn all of this heat into power output. Now, in the next few lectures here, we're going to try to work our way up to being able to quantify why that's the case. That's the second law dictates it. So in order for this process to continue, we have to reject the heat that we couldn't convert into power. We have to reject it out here into the condenser, and hopefully we're putting in just a little tiny bit of power input to increase the pressure of this liquid to the higher pressure so it's ready to run back in the turbine at a high pressure. We said that the first law, which basically says that the net power output, the difference between the work out and the work in, is equal to basically the net heat in, that's Q dot H minus Q dot L. And we said that the thermal efficiency for any heat engine is always going to be what you want, the net power output, divided by the rate at which you have to supply heat to get it. And we can massage this to 1 minus QL over QH. And all that to say that the Carnot, we talked about the Carnot cycle as one of the first reversible cycles proposed, and we found that the Carnot engine can, or that any engine we can construct cannot be more efficient than a Carnot or any other reversible engine operating between the same two reservoirs. Therefore, the efficiency of a Carnot cycle or any other reversible cycle is only a function of the temperature of the reservoirs. So the maximum efficiency occurs when I have a reversible cycle. A Carnot is a reversible cycle. Any other reversible cycle is fine. So the maximum efficiency occurs when I have a reversible cycle, and that is 1 minus the ratio of the low temperature to the high temperature. These are the only things that control the maximum efficiency of this device. And we said it can be the same thing with a refrigerator or heat pump. Those are essentially the same device, just repurposed. One serves a different but similar purpose. Right? So a refrigerator or heat pump, these are devices that are going to reject heat to a high temperature source using we put the condenser on top here. So using a condenser, that condenser is fed by a compressor. So I draw the reverse of a turbine, right? So something that I put work in or power input into, and fluid flows the opposite direction through it. A compressor is being fed by a set of what we call evaporator coils. Something where I can have low temperature refrigerant absorb heat from a low temperature source, absorb enough heat to cause all of the refrigerant to boil off, evaporate off, and then that's ready to run back into my compressor. And again, in between the two heat exchangers here, I've got a condenser on top, high pressure condenser, low pressure evaporator. In between the two, I have to have some device that allows for a pressure drop. A turbine will work here. We can actually put a turbine in here. We normally don't unless it's a really large refrigeration system. There's just not enough power here to harvest, but you can put a turbine in here and harvest power out as you drop the pressure. You wouldn't do that in a small residential refrigerator. That's just another moving part, and if the turbine breaks, the whole thing breaks. But I can put, typically what I'll put in here is what's called an expansion valve. No moving parts, similar to what happens when you hold an aerosol can open. It causes a pressure drop and causes a temperature drop. So that's both a refrigerator and a heat pump will look very similar to this. Excuse me. First law says that the work in is going to equal, and if we do it per unit time, that's the power input is going to equal basically the net heat out. That's going to be Q dot H minus Q dot L. This could be work in is equal to QH minus QL. We don't have to put the dots there. We only put the dots there if it's per unit time. Now, the coefficient of performance for a refrigerator is always going to be what we want, QL or Q dot L if you like, divided by what we have to do to get at the power input. And plugging this in here, we can massage this into 1 over QH over QL, dots if you like, if you want to use per unit time or total amounts either way, minus 1. And so the maximum coefficient of performance for this refrigerator would occur if I have a reversible device, Carnot or any other reversible cycle. That's 1 over the ratio of TH to TL. I was hoping to get, and we can write a similar set of expressions for the heat pump. We could do that. I think I can squeeze that in down here. It's a little tight, but we can get it. COP for the heat pump, that being Q dot H, my desired quantity, divided by W dot N. And that's equal to, plugging this in here, that's 1 over 1 minus Q dot L over Q dot H. And again, if I've got a reversible heat pump, COP for that reversible heat pump would be 1 over 1 minus TL over TH. Okay, first page. All right, so I've got on our slides here all of that information, just kind of quickly. I'm not going to show a whole lot of that. But again, just understand that if it's a reversible device, that means that's the maximum performance or maximum efficiency for that device. And a Carnot is a reversible cycle. So that's kind of the first proposed reversible cycle. All right, that's Chapter 6, kind of in a nutshell. For us, that's Chapter 6. That leads us to Chapter 7, where we start actually talking about trying to quantify the second law using a quantity we call entropy. Entropy, let's see here, entropy is a measure. Entropy is a measure of how much energy in a system can be converted into work. That's what we as engineers will use entropy for. It'll also show us whether something's possible or not. Historically, if you've had a chemistry course, and hopefully you have before you take a thermo course, we maybe have introduced the concept of entropy and said that this is a measure of the disorder, the chaos, how unpredictable are the molecules within your system. That's all true. What we know is when we talk about entropy, systems will spontaneously reach a higher state of disorder, a higher entropy. That's what they naturally, spontaneously want to do. If you want to get your system back to a lower state of entropy, you will have to put work in to organize the molecules to get them to where they will behave more predictably. In the case of a refrigerator, to cool the molecules down is going to require work to do so, okay, or power to do so, and that's the second law is the reason for that. That sets the limit for this. Now let's see here, what else have I got? Oh yes, our good friend Klaus is here. I've borrowed a picture from Wikipedia. I'm sure that's where that's from. I'm not going to talk in a German accent. I feel like that would just be offensive. But our good friend Rudolf Klaus is a German physicist / engineer, credited with one of the major contributions to the formation of the second law, the Clausius statement, which we talked about in the last chapter. Clausius also comes to the conclusion that if I have a cyclic, if I take a cyclic integral, if I add up everywhere, and again this is just a d, this is a partial d in this case, if I add up all of the tiny little differential size amounts of heat transfer divided by the temperature at which those heat transfers occur, I get a negative quantity. Well, where do I have a cycle? Oh, here's a cycle where I'm adding heat at one temperature and I'm removing heat at another temperature. And what Clausius is saying, if you go around this cycle, I guess in this direction, add up all the heats divided by the temperature at which they occur, you get this negative quantity. Right? It can approach zero, but it's always negative. And he tried really hard to get that cycle to approach zero, and that was kind of the conclusion, was as the cycle approached a reversible cycle, as it got better, as we approached the maximum efficiency, this quotient, this integral, this cyclic integral here would approach a zero quantity. Couldn't quite reach it. And so this was the conclusion, that the reversible, if it was a reversible cycle, this quantity would reach zero. And then everything else we could construct that's irreversible always generated a negative quantity when we added this sum up. All right, now where does this sign come from? How do we know, what do you mean negative, Steve? Well, if we assume kind of a traditional sign convention, and most thermodynamics texts will assume this, our text doesn't necessarily make this assumption at first. We just always say add the ins, subtract the outs, and that's still the same thing here. That's always true for heat. So under traditional sign convention, the heat in is always positive, and that's what we'll do here, is we'll say, well, if you're adding heat to your system, that's positive heat. So everywhere, go around your cycle, and everywhere you're adding heat to the cycle, here, for example, take that heat divided by the temperature, and that's a positive quantity. And then he's saying anywhere you're removing heat from the system, or the cycle, that would be here. Here we're removing heat, so we're going to subtract this heat divided by the low temperature at which it occurs. And again, he's saying that if I go back to the integral here, if you go around the cycle and add all the heat in divided by temperature, subtract all the heat out divided by temperature, the negative quantities will win out. They will have larger amounts of the negative quantities because you're dividing by a lower temperature in theory. Right? So it kind of sets a limit. And so Clausius came to the conclusion, well, a lot of times we will credit Clausius with being the father of the second law. So I always make this terrible joke, if you're doing your homework and you're absolutely hating your thermo homework, and don't be mad at Professor Fowler, it's not my fault, this guy. And go back and look at the picture of Sadiq Carnot, look at that guy. Those are the people that came up with this stuff, not me. Don't hate the messenger, but it's a terrible joke, I know, but I like to make it. This is the guy that you want to hate if you really want to hate. But I wouldn't. He's really quantified, figured out what can we do and what can't we do. And this is a very simplified version of the second law, and this is Clausius' conclusion. Clausius realized that he's measuring a quantity. He's measuring a new property. And today we recognize this property as actually the entropy of the system, or a measure of the entropy of the system. So if we take an amount of heat transfer, and there's my alarm, so that's actually going to be a nice stopping place. We'll pick up on the next video. Loud pop.